So this is joint work with Scott Aaronson, Alex Cojocaru, and Elham Kashefi. So our result is basically a complexity theory result. There will actually be very few things about quantum information theory in the result itself. So for that reason, I just want to give a very quick complexity theory prelude. So I'll refer to BPP as the set of those problems that can be solved efficiently by a classical computer. And by efficiently, I will always mean can be solved in polynomial time in the input size. BQP is the analogous class for quantum computers, so what can be solved efficiently on a quantum computer. And lastly, NP is the class of problems for which we can verify a solution efficiently. We can check the solution efficiently. Okay, so complexity theory is notorious for the fact that it's very difficult to prove that complexity classes are different from each other, except in very simple cases. So this is what we conjecture the relationship between these three classes to be. This is unproven, but we have very good arguments for why it should look like this. So these are, let's say, the main three complexity classes that I'll be talking about. But I also want to talk a bit about oracles. So oracles you can think of as black boxes that can solve certain problems. So as an example, this class, this notation, BPP to the NP, means we have a classical computer and he has a black box that can solve NP problems for it. So the classical computer, in a sense, can consult this oracle and get the answer to some NP problem. So whenever you see the uppercase notation, it means that's an oracle for something. So it can be an oracle for a problem or for a class of problems. So using this notation, the last thing I'll define is the polynomial hierarchy, which is the infinite union of all of these classes. So NP, NP to the NP, and so on. And each one of these is called a level in the polynomial hierarchy. And again, it's a standard conjecture in complexity theory that each level is strictly contained in the one above it. Again, this is unproven, but we have very good arguments for why we think this is true. So what people usually say here is that we believe the polynomial hierarchy doesn't collapse, because the picture we have is something like this. It's a tower, and each one of these is a level of the polynomial hierarchy. And of course, each level should contain everything that is strictly below it. Okay, so that being said, let me tell you about the crypto part. So suppose we have a client that we usually refer to as Alice, and this client gets some input x and wants to compute a function f of x, but the client will be restricted to BPP computations, whereas the function that she wants to compute in general might be more difficult than something that can be done in BPP. But luckily for her, there is a server nearby that has the ability to compute any function. And the server says, well, just send me your input x, and I will give you an evaluation of your function f. I'll give you f of x. But of course, the client is reluctant to do this because her input might contain sensitive information like medical data, military secrets, whether Trump colluded with Russia, stuff like that. So she's very reluctant to give her input to the server. And so what she will do, and what we've seen in previous talks, is that she will compute some encryption of the input x and then send this encryption to the server. And then in contrast to fully homomorphic encryption, where there should just be now one reply from the server back to the client, in this case, we'll assume that there's a number of interactive messages, a number of messages being exchanged between the client and the server. And we also require that the only thing the server learns about the client's input is its size or an upper bound on its size, but nothing more than that. And we want this guaranteed to be true in an information theoretic sense. So no matter how powerful the server is, this should always be the case. And then at the end, the client can recover f of x as a result of this interaction with the server. So this thing that I've just defined or mentioned is called a generalized encryption scheme, and was formally defined in 1987 by Abadi, Feigenbaum, and Kilian. And what they were interested in determining is for which functions can we have such a protocol? For which functions can we have a generalized encryption scheme? So they gave a complexity theoretic characterization of those functions, but I won't go into that. So let's just think of those functions, the class of functions which admit such a protocol, as the class GES. And I should mention that this is actually a superset of all functions which admit such a protocol. So functions for which a generalized encryption scheme exists can be in this dotted circle over here. And what they give is a superset, so a set that is definitely containing all of those functions, but probably is bigger than that. But that's actually sufficient for their purposes, because what they wanted to show after this is how does this class relate to the class NP? So in other words, do NP functions admit a generalized encryption scheme? And what they showed is that no. So the class of NP problems should be different from this class GES of, well, an upper bound of what we can do with generalized encryption scheme, provided that the polynomial hierarchy doesn't collapse. So everything will be up to these assumptions, basically, that the polynomial hierarchy doesn't collapse or other complexity theoretic assumptions. Okay, so now finally talking about our work, we wanted to see how the class BQP of things that can be done efficiently on a quantum computer relates to this class GES. This is the first part of our result. And the second part was, in a sense, to quantize the Abadi et al. Result and see which functions would admit a quantum generalized encryption scheme, where this is something that I'll define later on in the talk. So let's focus on the first question. So if we had a generalized encryption scheme for BQP functions, then it would be exactly the same picture as before, except now the functions are restricted to being BQP functions. But everything else is the same, and presumably in practice we would delegate this to a quantum computer, but in the mathematical proof we assume that the server is unbounded in computational power. So before telling you what we think the answer to this is, although you can probably guess from the title of the talk, we can look at some related results. So if we slightly change the generalized encryption scheme, we actually find a number of positive results. So for instance, if the client has the ability to prepare single qubits, then it is possible to delegate BQP functions and have all of the other properties. On the other hand, for a classical client, if she's interacting with two entangled servers, then again it is possible to do all of that. Or if a classical client with one server but is leaking more than the size of the input, then again it seems possible to do that. And a very recent result shows that if you have computational security instead of information theoretic security, then again it becomes possible to do those things. But what we think is that for a GES proper, as I explained it previously, we think that the answer is no. And we give some evidence to support this, this conjecture that we have. And the evidence is in the form of an oracle result and a sampling result, which I'll explain in a second. So basically, these are results that are kind of supporting the conjecture that BQP, much like NP, should also be different from this class GES. Okay, so going back to the generalized encryption scheme, this was the scheme that we had. And I didn't specify, but this number of rounds of interaction with the server should scale polynomially with the size of the input. And actually, the size of the messages themselves should also scale polynomially. So we need to have polynomial communication there. But let's consider a slight change here and say that we upper bound the polynomials, so we only consider up to polynomials of degree d. And in this case, we can define the class GES of d for all those functions which admit such a scheme. And then, of course, GES itself would be a union over all exponents of the polynomials, so all possible exponents of the polynomials. Okay, so if we do this, then we can actually show that for each such exponent d, there exists an oracle, and this oracle will depend on d itself, such that relative to this oracle, so given this black box, BQP is different from GES of d. So the oracle itself is based on Simon's problem, and basically what the oracle does is you give it an index n and a value x, these are binary strings, and it gives you the evaluation of some function specified by the index on the point x. And the problem that we can define relative to this oracle, which is exactly Simon's problem, actually the complement of that problem, is to determine, given an index for such a function and access to the oracle, whether the function is one-to-one or has Simon's property, where Simon's property just means that the function is 2-to-1 and it has a certain periodicity condition. So this is a bit of an oversimplification because there's actually a bit more to it than that, but this is the basic idea. So we can use an oracle like this to separate these two complexity classes, but whenever we fix the degree of the polynomial in the communication. Okay, so moving on to the second part, the sampling result. Again, if we look at the generalized encryption scheme, we're going to change it again so that instead of getting the evaluation of some function f, what we're actually getting is a sample from a probability distribution. So in a sense, what the client is delegating to the server is a sampling task. So she wants the server to be able to sample from a distribution, and this distribution should remain unknown to the server. And then we want all of the other security guarantees. So we want polynomial communication and that the server only learns the size of this index x, which is specifying the distribution. So if we have this, then we can show that the family of distributions that can be sampled from efficiently by a quantum computer, which is SAMP BQP, should be different from those distributions that admit such a scheme, which is SAMP GES, unless there exists a family of Boolean circuits, CN, having the following properties. And you should really brace yourself for this. So one property is that the size of these circuits is almost exponential. It's not quite exponential, and that's actually really important. The second thing is these circuits can make queries to an NP to the NP oracle. And the third thing is these circuits compute exactly the permanent of an n by n matrix. So we think that the existence of these circuits is unlikely, although this is, in a sense, a much stronger assumption, the non-existence of these circuits, than something like, say, the polynomial hierarchy collapsing. And I should mention that our initial result in the paper, we thought we had proven this up to the polynomial hierarchy collapsing, but it turned out that that proof was wrong, and we weren't able to fix it, so we managed to prove this thing instead. And we're still in the process of updating the archive paper with this new result. But just to give you an idea of why we think this is unlikely, the best known result for exactly computing the permanent is Reiser's algorithm from 1963, which requires exponentially many operations, order n times 2 to the n operations. And basically, it hasn't been improved ever since, again, for computing the permanent exactly and for general matrices, because for particular types of matrices, there are improvements, and also for approximating the permanent, there are improvements. But our case is for exactly computing permanence of general matrices. Okay, so in the last few minutes, I'll also tell you about the second question that we focused on, which is which functions admit a quantum generalized encryption scheme. So what does this mean? It just means that it's the same as a generalized encryption scheme, but the first message is a quantum state. That's the only difference in the protocol. So everything else stays the same, but the first message, which in the previous case was the encrypted string, now is a quantum state. And the reason I have BPP star over there, the client can still only do BPP computations, but the star is indicating that she's somehow sending this quantum state to the prover, to the server in the beginning. Okay, so we know that these protocols already exist for BQP functions, and they're collectively known as blind quantum computing protocols. So this tells us that BQP is definitely contained in the class of functions which admit such schemes, which we'll call QGES. But what we were interested in is, well, how big is this class QGES? What extra power does that first quantum message give you? And what we found is that this class is rather large. It obviously contains BQP and GES, and again, we gave a complexity theoretic characterization of this, but I don't want to go into it. We'll just call it QGES. And the last thing we wanted to see is how this relates to NP. So the question is, if we now allow this extra ability of sending a quantum state in the beginning, is it now possible to delegate NP problems to the server? And we actually found that the answer is no. So NP and this new class should remain separate from each other unless a quantum version of the polynomial hierarchy collapses. So this can really be viewed as quantizing the Abadi et al. Result. And as I said, it basically shows that we can't use these quantum generalized encryption schemes like blind quantum computing to delegate general NP problems to server unless we're willing to compromise in other respects, like increase the communication to super polynomial or something like that. Okay, so to end, as I said, our paper basically has two big results. One is providing evidence for why we don't think BQP functions should admit these generalized encryption schemes. And this advice is in the form of an oracle result and a sampling result. And the second part was to define this quantum generalized encryption scheme like blind quantum computing and give a characterization for functions which admit such a scheme, and then showing that that probably does not contain NP unless the polynomial hierarchy collapses. So obviously, as future work, we'd really like to be able to base our results on weaker assumptions, and in particular to see if we can fix the original result with the collapse of the polynomial hierarchy for the sampling case of BQP problems. Okay, so that's it. Thank you.